So welcome to the 12th session. Next week we will finish the workshop. Today we are going to talk to revise chi-square Fisher exact test, student T test, and Anova test. We will also learn the new concepts of the test for normality. How can we find out if the data we have are normal or parametric enough to do the parametric tests, because the student T test, Anova tests, those are parametric tests, okay? And if they are not normal, we will move on to the non-parametric tests, okay? So remember those. Okay, now I need your help with this, okay? Can anybody talk about the types of data we have? Okay, let's start with the weakest, with the weakest type. Okay, the nominal data. We have either yes and no or several categories. Okay, those are named categories, categorical data. After that, they are not parametric. Okay, so we can't use t-test, Anova test for this kind of stuff. Okay, we can use chi-square. Okay, chi-square and those categorical tests are considered non-parametric tests, okay? Then we have the ordinal, okay? For ordinal, we have also categories, but the categories are defined like in a symmetrical pattern or an ordinal pattern, okay? So the highest one is higher than the lowest one, okay? In that measurement. Then we have the interval. The interval, we have like the temperature, any score, okay? We have like steps that we can move from one step to another step, okay? And then we have the ratio, okay? So the ratio are like how high is that person, blood glucose, other stuff, okay? Everything that is continuous is a ratio, okay? So those are considered parametric. So we can use Anova test, t-test, okay? But when we have those kinds of data, but they're not having that normal distribution, we are not going to be able to use the parametric tests, and we will use the non-parametric tests, okay? Is that clear enough? Okay. I want to ask you about the clinical scores, okay? Where do you think the clinical scores are? Like a stage, for example, the steps of coma. Ordinal, exactly, okay? So for these kinds of stuff, we can't use the parametric tests. We will use the non-parametric test. If you remember the data we have, okay, let's leave that till we reach there. Okay, so here we have the parametric and the non-parametric concepts, okay? The assumed distribution in the parametric tests, we use normal distributions, okay? For any other thing that is not normal, we will use non-parametric tests, okay? The variance. Usually, we need a homogeneous variance for parametric tests, but that is not a rule or a prerequisite for non-parametric tests, okay? They can be homogeneous, but that is not required, okay? Typical data, ratio or interval, here we have normal or ordinal or nominal, okay? The relationship here in the parametric tests, they need to be independent, Okay, what does independent mean? Maybe in the next slide you will see what independent mean. Okay, the parametric tests usually use the mean. Okay, but the non-parametric tests use the median. Why? Because when we have the normal distribution, we can use the mean because it represents the whole distribution. But when it is like right skewed or left skewed, when we have outliers here or outliers there, okay, can we still use the mean? The mean actually will deviate towards the outliers, okay, but the median will not. Okay, the median is not so susceptible to the outliers. So, and that is good for non-parametric tests. Okay, actually the conclusions we have from the parametric tests are stronger. Okay, but it is more simple when we are talking about the non-parametric tests. Okay. When we say that we are going to use a parametric test, okay, we didn't use that last time, but because we didn't have enough time, but we said, okay, we will try to use t-test and Anova test, okay, but usually before using these tests, we need to test for these four concepts. If they all apply to our data, we can use the parametric tests. If any one of them is not applicable to our data, we can choose. Okay, the normal distribution, and we will see how we will test for these assumptions. Okay, the normal distribution, if they are not normal, non-parametric tests. Homogeneity of variance, but remember, this is just applicable for ANOVA tests and for the two sample t-tests. Why? Because we will have two samples. Okay, we will have two variants. Okay, when we have two variants, the variance of each group should be similar to the other group. But when I have a one sample t-test, how would I like test for the homogeneity of variance? I just have one variance. Okay, keep that on mind. Interval data, it should be interval data. We can use ordinal data in here. We can't use like, okay, comma, sugar, sleepiness, or something like this. Okay, those are ordinal data. We can't use the parametric tests for them. Independence, okay? Independence means two things, okay? First, that the data are selected randomly from the normal distribution. I'm not biased in my data collection, okay? And the other thing is that we do not have overlap between our samples, okay? Our samples are independent from each other, okay? Our data collection is independent for each group. Okay, can anybody tell me about this table? Come on, guys, speak up. Okay, if I have a one sample t-test, okay, but my data are not parametric or right skewed or left skewed, okay, I will use the one sample will kozom test, okay, and this is the non-parametric test that is used usually for the one sample t-test. Of course, we have several non-parametric tests, okay, more than the parametric tests, but we will choose just one for each parametric test, okay, to be equal to the parametric tests we need to do. For the two sample t-tests, we will use the Mann-Whitney test. And I think you remember that from the distribution, from the algorithms, we learned about like 3 or 4 sessions ago, okay? The Anova test, Crusoe-Wallace test, okay? And you can see here what are the characteristics of these kind of tests, okay? Those are not so important because we revised them before. But remember, the non-parametric tests work on the median. Okay? The parametric tests usually use the mean, as you remember from last session. Okay, so we will move to the other computer where the SPSS is, but I want to ask you if you have any questions before we move on. Okay. Now, do we have? Yeah, we have a question about the chi-square test. Okay. Actually, I will open the tests we already did. Because that is faster. Okay. Here we have a table of the count. We have the expected count and the percentage. Okay, but we don't have a test. Here we have all the percentages available. Okay, but we do not usually use all of them. We just use the percentage within the row. Here. Okay. Here we have all of the structure that is available. Okay, we have 2 columns, 3 rows. Can we have a Fisher exact test in here? We can't. Okay, but we have the chi-square test. Okay, and for the chi-square test, in order to accept the p-value of the chi-square test, here we have the p-value. We should consider this. Less than 20% should be lower than 5. And usually, it's better to be 0. 0 cells expected lower than 5. Okay? So we can't use the chi-square test, and I need to change something. If you remember, we merged the categories. Okay? And when we merged the categories, this is for stratification, and this is not important. This is for the splitting file. Okay. It seems like I didn't save the file from the last session. Okay, but we have analyzed descriptive statistics. As you remember, cross tabs. We will take the uni to the rows. You can't put 2 variables in the rows and press OK because it won't be activated. Okay, now I took the uni and the faculty, and those are the variables where I put, where I just divided them into 2 groups. Okay, I just erased the other groups. What are the statistics we need to use? The chi-square. Okay, else for the cells, we need the Z values and we need the percentages for rows. Continue. Okay. So now we have a 2 by 2 table. We have the percentages and we have the Z values, which is the adjusted residuals. Okay. Here we have the chi-square test. Okay. For the chi-square test, 50% of the cells are lower than 5. Okay. So I can't use the chi-square test. Sorry, here. I can't use the chi-square test. Okay. But in here, when I have a 2 by 2 table, what can I use? The Fisher exact test. The significance of the Fisher exact test is 0.5. Okay, so it's not important, and I cannot reject the null hypothesis. Okay, but let's assume that the b value was lower than 0.05. Okay, what is the conclusion I have? Come on, friends. We discussed that a lot last session.
That the faculty affect the university, or the opposite, بس إنه في effect.
Okay, there is an association between the effect of the faculty and the effect of the university on each other. Okay, but I can't have any further information. But I can see here, okay, that the when the faculty is positive, the university is positive. Okay, in 87%. But when the faculty is negative, okay, when the university is negative, the faculty is positive in 100%. Okay, so what I expect is when the university is negative in this category, I have more those with faculty than those without the faculty. Okay, the example is not so clear, but you can consider any other variable. Okay, any other variable, positive and negative, like happiness, not happy, and eating something, not eating something. Okay, so in this table I can see, okay, not having the university will increase the probability of having the faculty. Okay, do you agree? Or the other way around? Okay, it doesn't matter. There's an association between the lack of university and the presence of the faculty. Okay, do you agree?
Yes.
This is what the Z value tell us. Okay, the Z value tell us that, okay, what is the difference of this number, the 9, or this percentage, the 100, from the expected count? Okay, it is higher than the expected count, but how much higher? They took the difference. Okay, for example, let's say they expected that the number in here is 6, but I got 9. Okay, 9 minus 6 is 3, and we divide that on the standard deviation of the first percentage, the 60%. Okay, then I have the z value of the 9, and the z value for the 9 tells us, okay, the 9 is 1 standard deviation above the expected count. Okay, so if it is 1 standard deviation above, is that so important to us?
Not really. There is
more
not.
than 2?
There is no different تقريبا.
Yeah, it's not so important. Okay, as you see. So I will not consider that. But as you remember, we did another analysis, as I remember, from between the faculty and Skype. Descriptive, crossed out. Okay, in here, what do we have? We have the chi-square test and we have the Fisher exact test. Which one will I use?
I can use both because there is no cells and with expected count less than 5, so
Okay.
I can use chi-square.
Okay, perfect. And the chi-square is significant.
Significant,
okay?
yes.
And when I can use both, they should be similar. Okay, I can't have like one is similar, one is significant, and the other one is not significant. Okay, so I have a statistically significant difference. But what is the difference? The difference is Faculty of Medicine make people name their Skype profile as blah more than the Faculty of Pharmacy. Do you agree?
Yes.
Yeah.
Okay. Okay, perfect. This is the chi-square and the Fisher exact test. Is there any question about them?
Nope.
Okay, so let's remember the comparing the means. Okay, what are the columns that are applicable to the first assumption for the t-test? Okay, let's think about it. I need continuous data, interval data, not ordinal data. Okay, so the ID is applicable, as I think ID 20 is applicable, random number is applicable. We move on. About interest, you remember how we classified interest. So do you think this is applicable to be used as a continuous?
It's ordinal, as I remember.
It's ordinal, exactly. We have 6 categories, and in each category we have that number. We don't have anything between them. Okay, it's exactly like a coma score. It's like any clinical score. So I can't use a t-test or an Anova test for interest. And as you remember, we avoided them in the last session. Okay. So we will use them for the non-parametric tests. And of course, that also is applicable for those experience, what percentage do you expect to attend, and so on. So we have these 3 columns. How can I use them? I'll take analyze, compare means, we can take the one sample t-test. I can use the sample, the whole column, and I compare it to another mean. Okay? I compare the mean to the column. This is a one sample. I have one sample and one mean that is known already. Independent sample t-tests. Okay? Then I need two categories to be like independent samples. Okay, I took it. I need the ID 20, for example. But what I need is a grouping variable. What is the grouping variable in your opinion? For example, university. The grouping variable is something categorical that can divide the continuous column to two groups. So I can compare the continuous variable in this group to the continuous variable in this group. Okay? So group 1 is 0, group 2 is 1, continue. Okay. So what do I have? I have the ID 20 for the uni 0 and the uni 1, 9 in this group, 14 in this group, the standard deviation, the mean, standard error of the mean. And here I have the, what is the Levene test of equality? If you remember, we left that for this session. Okay, so let's keep it away. For the t-test, where is the significance? Here. Okay, so we have a significant result either if I think that they have equal variances or unequal variances. Okay.
Yes.
Okay, perfect. So what else should I look at before I can take the results of this t-test? We just spoke about them like 1 minute ago, 10 minutes ago. Take your time. I will wait for your answer.
You mean the assumptions?
Yeah. Okay, what are they?
ما حفظته.
Like first of all, the data we took
should be
continuous.
Okay, continuous, and we have continuous data.
Also independent.
Independent, and we have independent data. Okay, those in the first university are independent from those in the second university, and the two variables are independent from each other. What else?
Normally distributed.
Yes, we need parametric, I think.
Parametric. Okay. Okay. So we need to test for parametric distribution, normal distribution. What else? Just one left. Remember.
They should be homogeneous.
Homogeneous, and by homogeneous we mean that the two groups have the same variance. Okay, so let's look at it. What is this test for?
It says it's for equality of variances.
Exactly. So if this test is significant, then we don't have equal variances. This assumption is violated, right?
Yes.
So this table makes no sense. What is the test I should do? The man with me, right?
Non-parametric.
Non-parametric, man with me test.
Yeah.
Okay.
Mm.
Okay. Okay. So this is the test for homogeneity, and we need to do here. I'm sorry, I'm just searching for something that can fit in the 5 minutes left.
How to get this summary button to appear on my laptop مثلا.
Summary button?
Yeah, the option.
Yeah, which option? Actually, I don't remember. I'm sorry. Here?
Yeah, analyze, compare means.
Don't mention that. It is about the version of the SPSS. Okay. So
Okay.
yeah, let's just revise the ANOVA test. If you remember that the ANOVA test is okay. Yeah, I just wanted to ask you a question. If I have, let's say we have a significant difference and we need to take that test, okay? Do we have any difficulty in understanding what is the difference? Like in chi-square, we were confused. There is an association, but we didn't know where is the association till we received the Z values, okay? And we say that we need a post hoc analysis, okay? But in here, do we have that difficulty? Faster. We
Didn't
have,
get the question.
okay, we have a significant p-value. What is the answer? What is the conclusion?
They have the same mean.
If it is significant, they are different. Okay.
Yeah, a
Remember,
significant difference.
the null hypothesis means they have the same mean. The p-value should not be significant. Okay. If the p-value is significant, then the means are different. Okay. But
Yes.
I need to understand more. Okay.
The university affects the ID.
Okay.
That's
How?
It may. Okay, if the university is one, then what?
The mean is lower. Okay. Well, we do not need Z values or something like this. Why? Because, okay, the university is not there, we have that mean. University is there, we have that mean. Okay, then we know which is higher than which. Right? What?
Yes, okay.
Okay.
Is that clear?
Yes, we keep thinking that we have to link this to some applicable information, like we're looking for extra meaning. It's just the way it is. It's a higher mean for each group.
This is the meaning we took from the chi-square, okay? For the chi-square, we had that table, but we didn't know which is higher than which. But here, it is so obvious, okay? But
Yes.
what I will do is analyze. Do you remember a category that was like a that has 3 values or more?
University, before we change it into.
Okay, university. Analyze. Compare means. We need the ANOVA test. I will take this dependent, and the factor is university. No, the university will not be here because it's not coded. We need something from those.
Okay, let's take the interest.
Just 1 minute. For those 0, 1 interest. But I think interest has many groups. Oh, okay. Okay. We shouldn't use it like this because it will compare two continuous scales to each other. But I remember to graduate, and I will move those to be okay. Now we have that column, analyze, compare means, one-way ANOVA, and we can put it in here. Okay, so here we have a significance, and you need to tell me about this significance and the understanding about this after the break. Yes, I agree. The ID is different between the groups, or the ID is not different between the groups. Okay, and what is the conclusion out of this? Do you remember, like for a Fisher exact test, it is obvious because we have 2 by 2 table. For chi-square, it wasn't obvious. We needed the Z value to understand the difference between the groups. For the t-test, it was obvious because we have one mean higher than the other mean. Okay, for here, what do you want?
The F? No?
Okay, you have the F. You have the F. Tell me about the F.
If it's close to 1, then نسيت. يا في difference أو ما في difference بس القيمة هي 1.
Okay, just we leave that table, okay? We return to the analysis. Okay, now we understand there is a difference or there is no difference. Okay, now what we need to go and do, and we usually do that when there is a difference, okay? It makes no sense searching for the difference that is not significant, okay? So let's assume there was a significant difference between the groups of graduation regarding the ID, okay? So here you have that the contrast, you don't need the contrast. You go to the post hoc. If you remember for chi-square, I told you for the chi-square we need the post hoc to understand more about the Z values and to tell, okay, this is increasing this, okay? Here, actually the Chuki test was not checked. And now what do we need to do is checking the Chuki, continue for the options. Let's check, we need the descriptors, we need, don't check the fixed and random effect, it is difficult to be explained right here. Let's check the other tests and mean plot, okay? And we press OK, and we see what happens. Okay, we have a lot of stuff in here. Let's start with the first one. Here, the one-way ANOVA, actually we asked him to give us the descriptors. The descriptors mean we have not a graduate, graduate, semi-graduate. Okay, the mean 200, 270, 123. Okay, so those are different from each other. Do you agree that this is enough? If I have, let's assume I have a significant p-value for the ANOVA tests, and you see those numbers, is that enough for you to assume, okay, the highest is the graduate, the second is the not graduate, and the last is the semi-graduate. Is that enough for you?
Maybe we should check for variances. Maybe we should check the Levine statistics.
We need to check more. Okay, let's keep saying that. Okay, we need to check further. Okay, so if you remember, we didn't just ask the ANOVA test to tell us about the descriptor. We asked him about different other stuff. Okay, so for example, the homogeneity of variance, the Levine statistics. Okay, do you remember it? Okay, do we need that test to be significant or not significant?
Significant.
Significant.
Why? If it is significant, what would that say?
We can do the test. If not, we can do the test. It's not.
Yeah.
We
It's
need
exactly
parametric.
the other way around. Okay, if it is significant, there is a difference in the variance. Okay, and we don't need that. So we need the Levine test to be unsignificant. Okay.
Yes. So
Yeah,
that it's not
just remember that, okay, when we are testing for this stuff, okay, for the homogeneity, for the normality, for this stuff, we don't need the test to be significant, because if it is significant,
then we can't use the ANOVA.
the data are not parametric. Exactly. Okay, what else do we have? The ANOVA test. You remember that test, okay? The significance 0.09, okay? It's not so significant, but let's assume for just a second, okay, it is 0.05, okay? If it is 0.05 and we have the means, we have, okay, we can, the Levine test is not significant, then we can take the results of the ANOVA test, okay?
Yes.
Okay, and we have those. Are we satisfied? Actually, we are not satisfied, okay? We need something similar to the Z test, saying that, okay, this is more than this by this Z value, okay? We need something similar to that, okay? So if you remember, we checked the 2P test. It's a post hoc test. Post hoc means like, okay, after I do the ANOVA test, post hoc, okay, let's understand what happened in the ANOVA test. ANOVA test told us it is significant. Okay, so let's look in here and see what is the significance. Okay, this table is actually complex. I hope you are seeing it clearly, but here the post hoc test, the 2P test, is saying multiple comparisons. Okay, first we have the not graduate. This is one of our categories, and it is compared to the graduate and semi-graduate. What this table is doing, like he took one of the categories and compared it to the other two. Okay, I took this, compared it to the other two. The mean difference from the graduate is this. The mean difference from the semi-graduate is this. Okay, the standard error and the significance. We don't have any significant result in here. Okay, so we know that the not graduate group is not significantly different from the graduated and is not significantly different from the semi-graduate. Although I have a mean difference, okay, it means that I have a difference, but the Z value is not so big. Okay?
Okay.
Okay. The second line, we took the graduated, compared it to the not graduated, and compared it to the semi-graduated. We have a mean difference of 68 and a mean difference of 154. Okay, and you see the significance in here for graduated versus not graduated. It's not significant. Okay, but for graduated versus semi-graduated, it's 0.07. Okay. Yeah, it's still not significant, but
Close.
so close to be significant. Okay. So if we assume that the ANOVA test is 0.05, then this comparison will be the cause of the difference. Okay. Remember, chi-square ANOVA test, they say there is a difference between the groups. Okay. But I need to understand which group is the different one from the others. Okay. So this is the way we need a post hoc for chi-square and a post hoc for the ANOVA, but not for the t-test or for the Fisher exact test, because we just have two groups and there is no need for this. Okay. For example, this table means nothing if I just have two groups. Okay. I will just have one line. Okay. If you go further, semi-graduated from not a graduate and semi-graduate from graduated, and it is just
information
nearly
from up there.
significant in the semi-graduated versus graduated. Okay, so graduated versus semi-graduated or semi-graduated versus graduated. So it is
the same but in different
the same
ways.
difference but in different line. Okay.
Yes.
Okay. Okay. So, and we have a p-value for this difference. Okay. We won't go into details in other tests, but let's see that. Okay. We said the difference is nearly to be significant between semi-graduated and graduated. We go here, semi-graduated and graduated. You see that line? This is significant. But this is not significant, and between not graduated and semi-graduate, it's not significant too. Is that clear?
Yes.
Okay.
Okay. We have three comparisons, three lines. Just one of them, which is between the semi-graduate and the graduated, is the one which is significant. Okay.
We don't have to understand that from the shape itself, right?
Of course, you will see that on the shape, but you need to understand the numbers and take the assumptions from this table, multiple comparisons.
Okay.
And remember that you don't go to this table if the original test, the one-way ANOVA test, is not significant
Not
at all.
significant.
It makes no sense to come here. Okay. So, actually, we talk about several normality assumptions and how to think about them. Okay, but we talked about them while we are talking about the t-test and while we are talking about the ANOVA test. And usually, I don't do the analysis, then think about the normality tests. I need to test for normality, and if it is normal, I can do the tests, or if it is not normal, I will do the non-parametric tests. Do you agree?
Yes.
Okay, so let's just for a while forget everything about t-test and ANOVA test. What do I need to do right now? I go to analyze, I go to descriptive statistics, and from descriptive statistics to explore. Okay, this is a new method. Okay, this is a new way to reach that analysis. Okay, what is the variable I need to test? I will test the ID. Okay, I need to see the statistics and the plots, because if you think about it, I will check the normal distribution. Okay, I can look at it in a histogram and see if it is normally distributed, and I can use tests to tell me if the data is actually normally distributed. So I will take both. Sometimes we just think about one, but now we are going to learn about all the methods of testing for normality, because this is the safest way, let's say. Okay, don't need to do an analysis and then our paper gets refused just because of the need of different analysis. Okay, I will consider ID as one group. Okay, let's for now think about ID as one group and let's test for normality in the ID. For the statistics, do I need anything in here? I will check the outliers. For the plots, what do I need from here? I need a histogram. Okay, I need a histogram, exactly. Here, you can see something that is exactly what we want. Normality plots with tests. Okay, is there anything that is more amazing than this? I don't think so. Okay, we checked it. We continue. Is there anything other than this? Okay, we don't need this. And let's press OK. Give it some time. And now let's start. Okay, we left in here. Okay, here they're just saying how many of the data are missing and how many are not. Oh, I'm sorry, there are 23 missing, so those are many. Let's just take a look. Okay, I will just delete the cases under this because it seems like they are considering them available cases. Okay, now I will just do the same test. Remember, from analyze, descriptive statistics, explore, ID, from plots. Okay, they are still checked. Okay. Now, where are we? Yeah, in here, we don't have any missing data. Okay, remember that when you have missing data that you don't actually think we have missing data, just go to the table, take your last observation and delete everything below it because it might be like spaces or dots or something like this, and SPSS is considering them as available cases without data. Okay, so now we have this. Okay, we have the mean, median, variance. Okay, we don't care about them so much. Okay, we care about skewness and kurtosis. Okay, can anybody tell me what is skewness and kurtosis? If I have that normal distribution, and this normal distribution goes to one side, and it is like down in the other side, then I have skewness, either this or this. Okay, if I have a normal distribution that is more tight or more flat, this is kurtosis. Okay, so what is the level I accept in skewness and kurtosis? Actually, it is the Z value. I need the Z value to be between 1.96 and minus 1.96. And how can I get the Z value out of this? I need to take it manually. Okay, I will take the calculator. I have a number for skewness in here and the standard error in here. Okay, so I just divide the skewness on its standard error. Okay, 0.026 divided by 0.217. This is 0.11. Okay, is it closer to 0 than +2 and -2?
Yes.
Okay, then I don't have skewness. Okay, the Z value is not so big, so the significance is not so big, and I don't need significance in here. Okay,
Okay.
let's take kurtosis. Okay, minus, no, sorry. Minus 1.234 divided by 0.431. I have -3. Okay, can I accept that?
No.
Okay, so
We have kurtosis.
okay, I have kurtosis. Okay, and I can do the parametric tests. Okay, let's assume, okay, the test just passed kurtosis. I have a small kurtosis. Okay, what do I need to look at more than skewness and kurtosis? Skewness and kurtosis are for what?
Normality of the...
For the normal distribution. Exactly. Okay. Actually, they invented a test that is a test for normality. If the data has any skewness, kurtosis, or anything, okay, the test will be significant. And this test is Shapiro-Wilk test. Okay, we have two tests actually, but this is an old one. We won't discuss it, but the important one is this Shapiro-Wilk test. Okay, do we need that test to be significant or insignificant?
Insignificant.
Okay, and it is what is it?
It is significant, so
Okay.
we cannot.
Yeah. We cannot use the
cannot say
parametric
it's a
tests.
normal.
Okay, what made Shapiro-Wilk significant? It is the kurtosis. Okay. The best way
Yes.
I suggest is that you check skewness, you check kurtosis, and you check the tests. Okay. We have time to do that all. Okay. Look at this ugly distribution. Does it seem like a normal distribution?
We should have like a higher levels in the middle and lower levels on the sides, right?
Okay, we need more data from 20 to 30, let's say, and few data, for example, after 50. Do you agree? Or lower than 0?
Yes.
Okay, we will try to make it normal after a while, and it is important to like see normal data. Okay, let's look at this. Usually, what we need is data that is actually hugging that line. Okay, so we are deviating a little bit, but it's not so obvious in here, and that's why we need the tests, we need the skewness, the kurtosis, because when we check all the criteria, we will be clear if we can use the parametric tests or not. Okay. The trended normal QQ plot. This is called the normal QQ plot, and here we need the line to be hugging the points. Okay. In here, we do not need it to be like this. We need it to be like moving like zigzag around the line. Okay. Those are okay. If you just look at the QQ, you will assume we have normal distribution. Okay. Because they actually look like a normal distribution, but we actually don't have normal distribution. Okay. Let's look at here Do we have outliers? This is called a box plot. Okay, here is the mean, the intra-quartile range, and here we have the upper line and the lower line, and we don't have outliers. Okay,
We don't
why
have
we don't,
skewness.
we don't have skewness? Yeah,
Mm.
we just have kurtosis. Okay,
Yeah, so there's no
all the data
outlier.
are in here. Okay, we don't have the tails. We need the tails to be to have the normal distribution. Okay, and when we don't have the tails, what do we have? Okay, we don't have the outliers. Okay, usually we need like to see like outliers here, outliers there, or so. Okay, because those are the things we should exclude. But here we don't have outliers, we don't have the whole tails. Okay, so one of the tests for the normal distribution is removing the outliers or thinking about them. Okay, and here we do not have either the outliers and we don't have the tails actually. Okay, we will try it on a different column. Let's take the random number. Analyze, descriptive, explore. We will just take the ID and remember that you can take several columns, okay, and test them simultaneously. Random number. Okay, let's see here. Do we have skewness without taking the calculator? What do you think?
Yes.
Yes.
Fine.
A lot of skewness, a lot of kurtosis.
Yeah.
Okay.
Yes.
Look at this. This is not skewness. This is the definition of skewness. We have all the data in here, and we have some data in here. Okay.
Yes.
Okay, and the Shapiro-Wilk is significant. So we are 100%. Look at this normal QQ plot. Do the data hug the line? And there is no hugging at all, right? Do we have any zigzag in here? No zigzag.
No.
So what are we saying? These data
Is not parametric.
are so far from being parametric data. Okay, for the last one, they were like nearly parametric data for the QQ plots, for example. Okay, look at this. Do you remember what was this?
Yeah, we had like all the data like a block in the middle before.
Yeah, exactly. Here we have the box and their lines, and all of those are outliers. Look at this outlier that is standing at 80,000. Okay, so I will check for those and I will remove them and I will test again. What do you agree? Look, I immediately found it. 80%. I will move it to 3. Okay, 80,000. I will sort ascending. If you remember, all the kurtosis was for higher variables, okay, and those were there. Okay, so I will make 100, 200, 300. Well, we don't usually play with data like this, but we are like
We select cases, right?
What?
When we have outliers, we select cases. Like we just cross them out from the analysis.
You need to think about them and treat them in the way you find suitable. Okay, sometimes the data entry is false. Okay, it is 8 and it is entered like 80. Sometimes, okay, you just need to consider them. Is it actually an outlier that is out? Okay, we just report it on our, for example, if I can't cross it out and I'm sure about that number, I tell them about that person, and I tell them that I excluded it from the analysis, so I get like a parametric data. Okay.
Okay.
Okay, I will do the same test now. Descriptive, explore for random number. Okay, look at kurtosis. I still have skewness, but no kurtosis right now. The kurtosis was just caused by the outliers. Okay, the data are still skewed. I still can do parametric tests. Okay, but I get rid of the outliers. Look at this. This is how skewed it is. Okay, now we have one sample that is not skewed with a lot of kurtosis, and this is not, it doesn't have kurtosis, but it has a lot of skewness. Okay.
Okay.
Okay. So for all of those, we can't use the parametric tests. Do you agree?
Yes.
Okay, we will try to make the ID parametric or normal distribution. How can we do that? We need some data from 10. Okay, I'll try it right now. Analyze ID, and we will see that it is at least closer to being a normal distribution. Sorry, descriptive. Explore. We will take the ID. Okay, I still have some kurtosis. I tried, but my attempt is not so successful. And it was like 0, 0, 0. I have now 0, 0, 1. Okay. What I did is that I increased some data around before and after. I removed some from the middle. Okay, but I'm not that successful. If you remember, it was just a flat. Okay, now it is a little bit closer to be a normal distribution, but it is still not a normal distribution. Okay, so now do you know when to use the parametric tests and when to not use the the parametric tests? Those are the tests for normality. And don't forget to test for the homogeneity of the variance, okay? When you use a t-test and an ANOVA test, okay? You can just see the Levene test and it is obvious. If it is significant, it's not a parametric data.
Usually we start from here, right? Like we have our data and then we do the normality tests and then we decide what tests
test?
are we going to use. Not like we did it.
Exactly. But we did it like in the best way to our understanding. But now you can link the information and understand what to do and what to not do.
Okay.
Okay. Is everything clear?
What can we do? Yes.
Yeah. Yes, please.
What can we do when? Oh, nothing.
Okay, so we will just do one of the analysis that is for non-parametric data. Okay, because we don't have time. I think we will just devote some time for these data in the future, for these tests in the future, in the next session maybe. But now we will try at least one of them because we still have 3 minutes. We'll take non-parametric tests from analyze non-parametric tests, okay? What do we have? Independent samples, one sample, related samples. When you look at them, what do you think about related samples, paired t-tests, okay? Independent samples, two sample t-tests, independent samples t-test. One sample t-tests, okay? So they actually match the ones from compare means, but they are not parametric, okay? And here we can like take more out of for like more than two groups, okay? Let's take independent samples. Okay, just leave those because maybe we discuss them next time, but we won't have a lot of time to do them right now. We will take the two independent samples from here, okay? They are actually the same, but this button will take less time. Okay, two independent samples. I will check the IT. Because it's not parametric, we found that we have kurtosis in here, and I can't change the data. So, and what is the grouping variable? The uni. Okay. Define 0, 1. Continue. What do you have in here? Man with me, you test. Okay. This is what we need. Options. Descriptives, continue, okay, and here we go. We have the number in the of the data that has ID and the number of data that has uni. Okay, for uni 0, we have the number of 9. For the uni 1, we have the number of 40. Okay, and we have the Z value in here and the significance in here. Okay, it is actually significant. Okay, so the ID is different.